Hello, it's a special treat to be sitting here with Dr. Ian Lipkin, professor at Columbia University and the lead of the new center, the NIH-funded Center, Center for Solution for ME/CFS. Thank you for being here.
My pleasure.
So this is a rare opportunity because you are a hard person to find. You are very busy. You travel all over the world. You are involved in Zika work. You are involved in any health crisis around the world. Set the stage up for us with respect to your
I've been doing this for a long time.
Yeah.
Really, when I decided to leave clinical medicine in 1985 and begin to work in basic science, which I'd really not done. I'd only taken the requirements to get into medical school, and then I finished these residencies. I found myself interested in trying to understand how people became ill, not just what I could do about it initially with the current armamentarium, but trying to find real solutions like you're trying to do with Solve ME/CFS. I had to go back to the lab, so I spent 6 years learning the tools of the trade, pipetting, early days of nucleic acid hybridization.
Cesium chloride, probably you did that, the whole thing?
Cesium chloride and conidinium and lots of radioactivity. Remember those days?
Absolutely, I do.
That was what we did. We all radiated ourselves. It was the only way to...
That's the only way to get healed.
To image anything.
That's right.
So, and then I found myself sort of moving directly into the use of genetic methods for detection of infectious agents. And that's what really led to my first exposure to ME/CFS, and which was then CFS. It wasn't even CFS in those days. And then the XMRV experiments, and ultimately where we are here today. And the focus of our center is on discovery. Because we think at this stage, this is what we need to focus on.
Yeah, so center discovery.
So our center is really focused on discovery. We've collected samples over a period of several years with the support of the NIH and the Hutchins Family Foundation and the Microbe Discovery Project, which was kicked off by the late Vanessa Lee, wonderful young woman who was dedicated to trying to find solutions, and she took her own life, as you know, in February of 2015. Because she was despondent about her condition. And we've gathered, great people to work with us, Oliver Fien at UC Davis and John Greeley, who's located at Albert Einstein, and this terrific clinician group that's really been with us since the earliest days of XMRV. You've interviewed all of them here, I think, with the exception probably of Jose Montoya, who I haven't seen at this meeting. And we're going to be mining these specimens as rigorously as we can, looking for signatures of viral, bacterial, yeast exposures, doing metabolomic, proteomic analyses, and moving into epigenetic and functional genomic studies.
That's wonderful.
Yeah, so it's
that's wonderful.
We're very excited.
Well, us too, and we will circle back to the collaborative research centers. I always find it very admirable about you in that you deal with big ticket items. You deal with national crises, right, on Zika, on Ebola, and things at that level, at that nature.
Well, the thing
but at the same time, you do the ME/CFS. So I want you to...
The thing right now, the thing that we're doing right now, which is absolutely devastating, is we're working with the Indian government, the Indian Council on Medical Research, with the most disenfranchised people I have ever seen. These are the Musahar. These are the lowest level socioeconomically of the Dalits in Uttar Pradesh, just south of the Nepalese border, and their children are dying of encephalitis. Thousands of them are dying of encephalitis, and so we've been going back and forth there and trying to figure out why these kids are ill, and there are a whole range of viruses and bacteria that are implicated. What we need to do is to identify not only how these children are getting sick, what are the pathogens, but how they're becoming exposed. So we do many things in our center, ranging from acute diseases like the encephalitis I'm talking about, as well as more chronic conditions which are equally challenging, more so in fact, because sometimes the trigger is remote. It might have happened years earlier. But the thing that attracted me to this field initially was, in addition to meeting Dan Peterson and having him send patients to me really in 1984,
early on, right.
so that's a long time ago, was that so many patients will relate to you that at some point they had an infectious disease, or what sounded like an infectious disease. And that then resulted in fatigue that just didn't dissipate. It continued, and it continues for years. So the question is, how do we find those fossil, imprints that allow us to detect infections that might have occurred remotely? So it's more challenging, but I think we can get there. I really do. So we've done this recently with autism, where we found that triggers of innate immunity during pregnancy place children at greater risk for autism, and I'm sure we can do it here. It's a question of bringing all these new techniques to bear. Now, what we're trying to do is to exploit, and I think that's the correct term, the various platform technologies and insights that have come about through emerging infectious diseases and biodefense research to bear on these other problems. So it's a peace dividend, if you will, from some of these other programs with which we've been involved.
On biodefense, after 9/11, you developed a national consortium of sorts, put together a group of leading centers. Is that technology helping in ME/CFS? Is that interdisciplinary work, even in encephalomyelitis work now in India? Has that been applied into the knowledge, at least?
So I think the pivotal moments were initially, of course, HIV, because everybody became aware that an infectious agent could spread, and that we had to find more rapid ways to identify these agents. But then there was West Nile, and what West Nile did for us in '99 was demonstrate that there were agents that existed in animals that could move into humans, and that we needed to pay more attention to what we think of as zoonotic diseases. That was certainly not the first zoonotic disease, but that's the one that captured the attention of the Senate and the Congress and pushed that forward. And then
why was that, Ian? Why?
Because there was a senator in Connecticut named Joe Lieberman who was concerned that it had taken so long to figure out what was going on. There was no conversation between the veterinarians and the human side, and so they didn't realize that the two were linked. So that was '99, and that's been, I've written about that, other people have written about that, so I won't dwell on it much. But after 9/11, when there was a recognition that there was, more than just, the mechanical risk associated with these horrific, explosions, and more, the anticipation of really what we've seen in terms of the breakdown of social order over the past few years. There was also the anthrax attacks, and the anthrax attacks, shut down, the Senate office building, and
came just after 9/11,
just after 9/11.
Right.
And so the government decided to invest in biodefense because we really didn't have a strong biodefense agency platform at all. So, there was a point at which the United States, like everyone else, was engaged in biological warfare research. Now, during Richard Nixon's administration, and people find this hard to believe, he decided to unilaterally declare a moratorium on offensive biological research. And he was a Quaker, so it was like the last sort of vestiges of his Quakerism that sort of came forward and said that this was inappropriate. So we didn't have a lot of work on the offensive or the defensive side. So from a standing start, the decision was made, and the leader really for much of this really was the director of NIAID, Anthony Fauci, who persuaded then President Bush that the money should not be allocated to this new Department of Homeland Security to do this research, but the U.S. scientific research community should be engaged to do this, and that they would do it better. The scientists should lead this, and as a result, funds were allocated to create centers. Now, the center I directed, which was in Health and Human Services Region 2, included all the institutions in New York and New Jersey, and the Virgin Islands and Connecticut, and Puerto Rico.
Puerto Rico.
But Yale decided to go with us.
To join too.
Rather than stay with HHS Region 1, Harvard, which I know is sort of your affinity, but what can I say? Anyway, because they got a better deal with the New Yorkers.
With you, yeah.
With the New Yorkers. Anyway,
Right.
we had a round table. Everybody participated, and we went as a country in a period of 5 years from having nobody doing this kind of research to having spectacular work.
Wow.
And it was all in diagnostics and vaccines and therapeutics. And all of these tools, right, which accumulated over the period of about 15 years now, are being brought to bear, on ME/CFS. So if there's an infectious agent, you know, people are going to find it now.
They'll find it, yeah.
And if their imprints somewhere in our experience, immunological experience, we will find that too. I think that ME/CFS is not a single disease. There are going to be subtypes within it, and there will be a subtype who will respond to drugs that are directed against viruses. There are going to be microbiome-focused, you know, efforts. There are going to be things that affect neurotransmitters. I mean, it's, you know, we're looking at, you know, it's the old story about the elephant. You know,
Yes.
one person touches it, this part, and says it's, you know, it's a tree, and somebody else
trunk.
touches this and says it's a rope.
Right.
It's all of those things. We need to understand the syndrome and of all of its complexity if we're going to bring solutions to bear.
But you think even in all these subgroups, there is a pathogenic construct to them?
I think there's a pathogenic construct to them, and I think there are obviously key features that allow us to lump. So it's very useful for certain purposes to lump, and others it's more useful to split. Right. The whole point of precision medicine, you know, which is a huge effort right now globally, is a recognition of the fact that we are all different in some way. That doesn't mean that, you know, that people are inferior or superior. It's not that at all. It simply means that certain genetic programs differ, certain proteomic programs differ, and if we can dissect those specifically, then we can identify the appropriate therapeutic intervention and the appropriate preventive measures. And,
Yes.
and that's really where the research needs to go. You know, I have been thinking about this set of disorders since I saw my first patients in 1984. And I knew then, and I know now that, you know, that they have been neglected, and this is something that I think is finally starting to change.
Yeah, because of you, and others in the field.
Because of others. Because of the field. Solve ME/CFS has had a huge role in promoting awareness, and without awareness, there will be no investment.
That's right.
And without investment, there are no solutions.
That's right. That's right. And thank you for your kindness. Now, these viruses, you know, let's explain to folks who are not scientists out there. These viruses work with cellular counterparts, with human cellular counterparts. So they need two to tango, right? So they either hijack our replication machinery, or they internalize themselves into our cells. We lost the microphone, but that's fine. So they always, you know, when we say viral infection, or there is a human cellular component to this as well. And many viruses sometimes target the same replication machinery for their own, the same factors in the cell. So because of the many viruses that have been associated with ME/CFS, does that tell you that there is a singular cellular counterpart? There are many cellular counterparts? Is that some avenue that we should be looking at more in terms of the classic replication machinery that is the bread and butter of viral propagation?
So, first of all, what are viruses? Viruses are not alive in the way we think of organisms as being alive.
Yes.
Bacteria, for example, can live outside of a cell. They just need nutrients, they need the right conditions, and they can grow. Viruses, as you say, are obligate parasites inside of cells. They must live inside of cells. If they're not inside of cells, they can't reproduce themselves. They can exist outside, obviously, because they have to transfer
Right.
from host to host, person to person, animal to animal, or plant to plant. But they can't reproduce themselves unless they're inside of cells. There are many different lifestyles for viruses. Some viruses go inside of cells and take over all the cellular machinery, make millions of copies of themselves, and blow the cells apart. And then they look for the next victim and they move on.
Right.
Other viruses are more subtle. They move inside of a cell, they take a little bit of this and a little bit of that, and they just sort of poke along. Those viruses can actually be as damaging as the ones that explode cells. Why? Because what they do is they interfere with your ability to function. So you can envision a situation like with a herpes virus, and there are many different types of herpes viruses, where it simply goes inside of a cell, and as a result of its life cycle, it reduces the amount of energy that you have, it interferes with your ability to think, it may have some sort of an impact on the immune system, resulting in an autoimmune disease, it can induce cancer. There are all sorts of ways, scenarios that can emerge from these types of infections. And bacteria and viruses can act in concert to cause disease as well.
Patches, all that.
So the only way to get at this problem is to use a multi-pronged approach. One effort should focus on trying to identify the infectious agent at the time. You may be able to find genetic material, proteins, you may even be able to recover infectious virus or infectious bacteria. The other is to look at the host response, because everything that you've seen over the course of your life is recorded in immunological memory. And immunological memory can be measured by the cells that make these little proteins called antibodies that attach to targets, or in the form of T cells. And T cells are cells that actually recognize other cells as infected, attack the foreign invaders in that fashion. So we need to be able to track not only immediate infection, which is present at the time you look, but the history of infection. The history of infection, if you use the appropriate sorts of mathematical tools, will allow you to make links between exposures and disease. And then the other aspect is you try to link all of these effects in some way, or many ways in some instances, to effects on metabolism. So energy production, cognition, affect or emotion, all of these things can be linked. And you do these using sophisticated epidemiological tools. So as we are in a school of public health, we have people who are used to doing this kind of work. So it really is, I think it's an ideal marriage of, public health, clinical medicine, basic science, and of course, everything at the end of the day focuses on the patients, because the patients are the ones who explain to you how they became ill, what factors aggravate their illness, what regimens appear to help them in some way. That's not to say that we rely on anecdotal evidence to make a definitive link between either a causative agent like a mold or a bacterium or a virus and the disease. We still have to do rigorous, objective research, but there are clues in the stories that you hear from people that allow you to say, I'm going to generate a hypothesis that I can test in a rigorous scientific way But that is based on the kinds of conversations that you will have with people.
With patients. And natural history of the disease in this space has been lacking.
It has. So another focus of this group, and I'm really privileged to work with these brilliant clinicians. So we have, you know, as part of our team now for 5 years, we've had Cindy Bateman and Sue Levine and Dan Peterson and Jose Montoya. Nancy Klimas is not part of our group, but she was very helpful early on. And of course, we have, you know, the maestro himself, Tony Komarov.
Of course.
Right, who's directing our clinical project with Dana March. And Dana March is an epidemiologist who has been doing very nice work with the Hutchins Family Foundation. And so she and Tony have created an app which is going to be useful in tracking how people feel on one day or another. This can actually guide us for sampling, so that perhaps we'll be lucky and we'll actually catch this thing at the moment. And I will say again that your letter for us was sincere and inspirational and extraordinarily helpful, and we deeply appreciate the opportunity to work with you and your team.
Thank you. This means a lot to us. Thank you so much for all the work you do, and thank you for being in this field. Much gratitude to you. Thank you.